Hello, NEET aspirants. Welcome back. In today's video, we will delve into the intricacies of thermodynamics. Thermodynamics is a fascinating branch of physics that explore the intricate relationship between the heat and temperature and how they interact with different forms of energy. Unlike some other areas of physics that focuses on the tiniest building block of matter, thermodynamics takes a broader approach dealing with large-scale systems and phenomena. Picture a gas, for instance. Instead of getting bogged down in the movement of a very single molecule, thermodynamics simplifies things by looking at the measurable quantities like pressure, volume, temperature, mass, and composition. These are the practical observations that we can readily make, help us understand and predict the behavior of the gas without needing to track every microscopic details. Graph shows a variation in a state of water at different temperature and pressure at constant volume. Looking at the graph, we get a point called as a triple point. The triple point of a water is a specific temperature and a pressure at which water can exist simultaneously in three phases: solid, liquid, and gas as a water vapor. Then comes a critical point. At the critical point, the substance no longer experiences a distinct phase change between the liquid and gas. It exists in a single phase with the properties intermediate between those of a liquid and a gas. Now let us contrast thermodynamics with mechanics, another essential field of physics. Mechanics primarily concerned itself with the motion of individual particles or objects under influence of forces. However, thermodynamics shifts its focus from such granular motion to the internal state of a system as a whole. Consider the scenario of firing a bullet from the gun. Initially, the bullet gains kinetic energy and moves rapidly, but its temperatures remain unchanged. It is only upon the impact, when the bullet comes to stop, that its kinetic energy transforms into heat energy, affecting both the bullet and the surrounding material. In mechanics, when we talk about equilibrium, we mean that the net force external or the torque acting on the systems are zero. In the GIF, when the stones of a different sizes are balanced on each other, it is possible because the center of mass of these stones align along a single line, and torque acting on the system of rock is zero. Now let's delve into thermodynamics, where the equilibrium takes on a different meaning. In this realm, we define the equilibrium as a state where a system's macroscopic properties remains constant over time. Consider a gas trapped inside a closed rigid container as illustrated in accompanying GIF. Despite the continuous motion of gas molecule within the container, its pressure, volume, temperature, mass, and composition of the gas remain unchanged. We classify the gas as being in thermodynamic equilibrium. Let's break it down further. Within the container, the gas molecules are in constant motion. Despite this motion, the number of molecules striking the boundaries of the container remains constant, resulting in uniform pressure. Additionally, average velocity of the gas particles remains consistent, ensuring that the temperature remains constant as well. So, even though the gas molecules are in constant motion, the equilibrium state ensures that key properties like pressure, temperature remain unchanged over time, indicating a stable thermodynamic equilibrium. Whether a system is in equilibrium depends on its surrounding and the type of a wall separating it. Let's consider two gases, A and B, in separate container. If we put them near each other with an insulating wall between them, meaning no heat can pass through it, called as adiabatic wall, they reach the equilibrium without changing their properties. But if we replace the insulating wall with a conducting one, which allows heat transfer, called isothermal wall, both gases' properties change until they reach a new equilibrium state where their temperatures are equal, but won't have same pressures as earlier. However, volume of both the gases will remain unchanged. What is special about the thermal equilibrium between the two systems? Well, when two systems are in thermal equilibrium, their temperatures are the same. We will learn more about the temperatures in thermodynamics through the Zeroth law, which help us understand how temperature works in relation to equilibrium. The Zeroth law of thermodynamics is a fundamental principle that helps us how objects reach thermal equilibrium or the same temperature. Imagine three systems A, B, and C, initially separated by adiabatic walls, that is, insulating walls. Now, adiabatic wall between AC and BC is replaced by conducting wall or isothermal wall. Heat flows between them. The states of A and B changes until they are in thermal equilibrium with C. If we then replace the adiabatic wall between A and B with a conducting wall and isolate C, we find that A and B does not change the states anymore. They are in thermal equilibrium with each other. This observation forms the basis for the Zeroth law, which states that if two systems are in thermal equilibrium with a third system separately, they are also in thermal equilibrium with each other. This suggests that there is a physical quantity that is the same for systems in thermal equilibrium, and we call this quantity temperature, T. So, if A and B are separately in equilibrium with C, their temperatures are the same as C. This means that A and B also have the same temperature, showing that they are in thermal equilibrium. Through the Zeroth law, we formally introduced the concept of temperature. The next question is, how do we assign a numerical values to temperature? Thermometry helps us in answering this question. We will explore in the next session. So, we have reached a brief pause in this fascinating journey through thermodynamics. I am Avinash from www.genit.com, signing off for now. Keep exploring the mysteries and the mystic wonders of nature and join me in the next video where we will delve deeper into the topics such as heat, internal energy, and the work. Until then, take care and keep exploring.